very much. Mr. Cho very kindly allowed me this time to make a presentation to you about carbon bonding properties. What I'm not talking about is how is it that carbon atoms bond with one another, and this is a very important concept in chemistry. And the reason I'm interested in this is because, as you know, in this class I have a few students who are visually impaired. And I want them to be able to understand the topic just like you guys can understand the topic. However, you guys have an advantage, which is that you can see the pictures that are in your textbooks. Whereas my students, they have trouble seeing those pictures, and they have trouble understanding the three-dimensionality of the pictures that are being displayed. So what I've done is I've made some 3D models using my 3D printer here. I'm going to be passing these around to you so that you can see the advantage of this. I think it'll help you understand these things as well. So we're talking about the bonding properties of carbon atoms, and what that refers to is a process called hybridization. And I'll make that clear in just a moment. So here's a couple of things I wanted to remind you of. I know a few weeks ago that Mr. Cho covered the topic of electron configurations with you. Perhaps you remember him mentioning something called the Aufbau principle. Okay, and in the Aufbau principle, potentially he described that as a diagonal rule. Anybody happen to remember that? Okay, where you have 1s and 2s, 2p, 3s, 3p, 3d. I'm not sure if you remember all of that. But so to cut to the chase, here's the idea. The electron configuration of carbon, showing that there are 6 electrons, is 1s2, 2s2, 2p2. Right? That's what's known as the ground state or lowest energy level of carbon atoms. Okay. Now, as far as bonding is concerned, the most important part of that electron configuration is the last part of it. In other words, the one that has the prefix of 2 in front of the 2s and the 2p. Those are the electrons that actually bond between each other. And we call those valence or bonding electrons. And they're present in the valence or bonding shell. You'll notice that there are 4 of them. There's the 2s electrons, and then there are the 2p electrons. Okay, so let me show you what that converts into as far as our 3D models are concerned. Okay, this model is an example or representation of a carbon atom. You'll notice that in the center there's a sphere. Okay, that represents the 2s electrons, and then in each of 3 directions, the 3-dimensionality of this, there's an x orbital. Both of these, right? These are called lobes. Okay, both of these are what are called the p sub x orbital. Okay, then in this direction is what's known as the p sub y orbital, and then in this vertical direction is what we call the pz electron. Okay, so in the basic carbon atom, there are 2 electrons in the sphere that's in the center, and then there are 2 more electrons that are left over that can be randomly distributed in any one of these px, py, or pz orbitals. Okay, and now the reason why this works out the way it does, it's actually the solution of a really, really complicated equation called Schrodinger's equation. And it's a statistical interpretation. What that means is, as far as the s electrons are, the 2s electrons are concerned, they're more likely to be found in that region close to the nucleus in that sphere. And then the p electrons can be found in any one of these other regions, the px, the py, and the pz. Okay, now, however, to bond between carbon atoms requires a process called hybridization. And so what can happen is that the s electrons that are in the sphere in the center can combine with some of the p electrons to form new shapes. And so here's an example of a carbon atom that has been transformed by hybridization. You see the difference between the two? Okay, I'm going to be passing these around in just a minute so that you can take a closer look. So what's happened in this particular carbon atom is that the py and the pz electrons have remained where they are. They haven't changed. However, the px orbital has combined with that center sphere to form what's called sp hybridization. Okay, S and P, an s orbital and a p orbital combined to form this. And you can see how there's a difference between the two of them. Okay, now as far as bonding is concerned, right, if we have two of these sp hybridized carbon atoms, they can bond together in the following way. Right? This lobe, that's called the sp lobe of the one carbon atom, can combine with the sp lobe of the other carbon atom. And this is what I'm calling the sp bond, or sigma bond. We slide these over here like this. Okay, and so now we have a bond between these two carbon atoms that's along the axis of the between the two carbon atoms. Okay, that's called an sp, or a sigma bond rather. Okay, then we can take these other, the p orbitals with something that looks like this. Okay, these are two carbon atoms bonded together. Okay, there's a sigma bond directed between the two carbon atoms, and then every time we connect two of the p orbitals together, this is one bond called a pi bond, and then we have another two that are combined together, also called a pi bond. And so in actuality, what we end up with is three types of bonds, or three bonds rather. Okay, we have one sigma bond and two pi bonds, and that's known as a triple bond. This arrangement can combine with hydrogen atoms too. There can be a hydrogen atom at either end of the molecule, in which case then you would have a chemical compound which is C2H2. Okay, and that would be known as ethyne, E-T-H-Y-N-E. So anything that forms this kind of hybridization and bonds with a triple bond, again, is called ethyne, or an alkyne. Okay, and you can go ahead and pass that around. Be careful with it. Okay, now a second type of hybridization, and I'm sorry I had to print these out. I'm running out of plastic. I had to print these out in a smaller way, right, would be this one. Can you guys see this? Okay, you can see how that's different than this. Okay, here's your original carbon atom, and then here's what's known as an sp2 hybridized carbon atom. Now what's happened in this situation is that two of these p orbitals combine together with the s orbital that's in the center. And so we end up with this interesting arrangement. And these combine together also. Okay, now, however, you can see that the p orbitals, there's only one of the p orbitals left behind, and so we can join them together. Okay, so that's once again, two carbon atoms that are combined together. Right? There's a sigma bond in between the two carbon atoms, and then these two things at the top and the bottom represent one pi bond. So in this case, we have a double bond between the carbon atoms. And any arrangement like that, where there's a double bond between carbon atoms, is known as an alkene. So I'll be passing this around as well. So you can take a look at that. Okay, you guys understand what I'm talking about so far? Okay, so two carbon atoms can bond, right, with triple bonds, in which case they're called alkynes. Two carbon atoms can bond with a double bond, and that's called an alkene. And then finally, there's what's called sp3 hybridization. Now check this one out. It's radically different than the original carbon atom. And what's happened here in this one is that all three of the p orbitals have combined with the s orbital. And it forms these four lobes that are actually in the shape of a pyramid. Right? And each of the lobes is an angle of 109.5 degrees away from the other lobes. Okay, in this situation, what can happen is that all four of these lobes are able to bond with say, hydrogen atoms, for example. So if this carbon atom bonds with 4 hydrogen atoms, you end up with a compound that all of you come into contact with every day, which is called methane. So any carbon atom that forms this sp3 hybridization is called an alkane. And an example would be methane, which is a combination of 1 carbon atom with 4 hydrogen atoms stuck on the end. Okay, so perhaps I can pass this around also. Yes, go ahead, next slide. Thank you. Okay, so just to kind of review and give you pictures of what I'm talking about. Okay, I don't know if you can see this, but here's an example of 2 carbon atoms. The 2 carbon atoms are joined by a sigma bond between the 2 carbon atoms and by 2 pi bonds. So that makes a triple bond. Okay, and then if you have 2 carbon atoms that are in sp2 hybridization, you end up with a sigma bond between the 2 carbon atoms and then 1 pi bond, right, leaving room for hydrogen atoms to connect on those other lobes. Okay, and finally, right, the one that's being passed around now, the one that with the 4 big lobes, that's called sp3 hybridization. And so you see that the lobes are separated by an angle of 109.5 degrees. Okay, now the reason why this stuff is so important, I think something like 90% or 95% of all of the chemical compounds that are involved in metabolic processes, in other words, things that take place inside your bodies or in the bodies of other organisms or like plants and animals, right? Something like 95% of all of the chemical compounds are one form or another of all these different things that you see here, right? And this type of bonding is really very much involved in the structure of things like DNA and various enzymes, all the stuff that's involved in life processes. And so there's a whole range of chemistry called organic chemistry in which these types of bonds figure prominently, very important. So I just kind of wanted to give you an introduction of all that and give you an opportunity to take a look at the models and see how that stuff worked out. So this is what I've been doing for my students, and like I said, I've been using this printer. I hook it up to my computer, and I've been using an open source computer design program called OpenSCAD or OpenSCAD, which is very accessible. It's easily used by anybody who understands the little simple geometry. So I'm usually down in room 111 if you want to talk about this or you have further interest. I'm certainly happy to see you and show you how this works. Anybody have any questions? Okay, well, thank you very much for letting me yammer at you. I really appreciate it.